Hey everybody, and welcome to our Praxical live science seminar. So we're very lucky we're joined here today with Armand, who's a scientist from ANSTO. So before we begin, I'd like to acknowledge that this seminar here today is taking place on Dharawal land in the south of Sydney, near ANSTO, and we'd really like to acknowledge and pay respects to the elders past, present and emerging. We also really like to celebrate the Indigenous people of Australia as the first people here, and as well as the first scientists who've been exploring the natural wonders of this great land for a very long time. So as I said, we're very grateful to have Armand here today. He's a scientist that's been collaborating with us to create the air pollution workshops that hopefully all of you would have completed by now. So without further ado, we're going to introduce Armand. He's going to tell us a bit about himself and what he does for his research and why he's so passionate about it. And then we can jump straight into questions, because this whole seminar is all around getting you the opportunity to answer, to get your questions answered by a scientist. So you can submit questions in two different ways. You can either submit them via the live event Q&A box, which should be on the right-hand side of your screen. If that's not there, up in the top right corner of your screen, there should be a little question mark inside two chat boxes, and you click on that to open them up. So throughout the entire seminar, feel free to write any questions you might have in there, and we should hopefully get around to answering all of them. We've also sent a few Google Forms out to people, so you can answer those as well. You can put some questions in there as well, and we should be able to answer them. So from here on out, take it away, Armand.
Hello, everybody. Thanks for joining us. It's really good to see that there's some interest in the science that we're doing at ANSTO, and particularly air pollution. A little bit about myself. I have worked at ANSTO now for 15 years, the last 10 years of which has been particularly focused on this air pollution research, but the area that I work in is the Centre for Accelerator Science. So we use particle accelerators to study air pollution, but can also be used on a range of other samples, everything from archaeological samples, material samples, so semiconductors, forensic samples, all the way to zoology. So one of the longest running research projects has been on this air pollution, as you've seen from the workshop going back to the 1990s. So that's what I've been working on. My background is in actually material science. So I studied material science at university. My PhD was in material science. I was actually looking at the next generation of solar materials. And then when I joined this group at ANSTO, I came into this area of air pollution and got very interested in it. So I've been pursuing it ever since, but as well as supporting a lot of the other research. Because ANSTO is a national facility, we have a lot of researchers from university come to use our equipment as well. So I help them run their samples as well. So I guess I'm not sure if there's any other questions.
Yeah, definitely. So thank you so much for that intro, Armand. That was very interesting. So the first question we have has come in from our Google Forms, and it's asking all around, how do you sample these materials, the filters that we're studying in these workshops? So as you would have seen in the workshops, they have these tiny little Teflon filters that they get the air particles to stick to that they can then analyze. We went into a tiny bit of detail about how this works, but some people have been asking, how exactly does that process happen? So Armand, if you wouldn't mind just telling us a bit more about that process.
Okay, so one of the unique things about this research project at ANSTO with air pollution is that we cover the full range. We go from the very beginning. We actually build our own samplers on site at ANSTO. We then take those samplers and install them in locations. Now, the way those samplers work is that they have a cyclone inside. It's like a cone or a funnel. So there's a pump that pulls air into this cone or this cyclone, and the particles spin. And the heavier particles fall down. So the particles greater than what we call PM 2.5, which is a particle diameter of 2.5 micrometers or less. The particles bigger than that are heavy and they fall down, and the centrifugal force pulls the lighter particles up, and they get pulled through this Teflon filter. And if you saw in the video, these Teflon filters, they're 25 millimeters in diameter, and they start off white. And as the particles are collected onto those filters, as the air is drawn through, in some sites, they can turn quite black. In sites that we study in Asia, for example. So in Australia, we pull this air through the filters for a 24-hour period. In some sites in Asia, they can only go to 8 hours before it's completely blocked. Sometimes 12 hours before it's completely blocked. So they have significant levels of pollution. And so we collect those filters from sites all around Australia and into Asia, and they get posted back to ANSTO. And every month we analyze those filters, about 200 or 300 of those filters from all the sites on our accelerator. And then the accelerator shoots ion beams at the filters. And those ion beams interact with those particles that have been collected. And depending on the type of interaction of those ion beams, we get X-rays that come off, we get gamma rays that come off, we get backscattered particles that come off. And we have a series of detectors around the chamber where the sample is in our accelerator. And those detectors can very sensitively measure those X-rays, those gamma rays, those backscattered particles, and they tell us what elements are in the sample and how much of those elements are in the sample. And that's what you saw with the data set. You saw some of those elements like lead and silicon in the data set you worked on.
No, thank you, Armand. So we've had a few questions come in, especially one from Veer, and it's all around what powers that particle accelerator. So you say it was an ion beam that you shoot at your samples that can excite them or get some different kind of particles bouncing off that you can analyze. But where does that ion beam come from? Okay, so that ion beam comes from essentially we ionize a gas. We ionize hydrogen. So we use electrons on a hydrogen gas to charge the particles. So the hydrogen particles, we charge them negatively. And then we use a static electricity, basically, to build a high voltage in the accelerator in what we call a central tank. And that high voltage is a high positive voltage. So those negative ions that we generate of hydrogen get attracted to that very high positive voltage in the center of the tank, and that accelerates them to that point. As they go through this accelerator tank, we actually strip the electrons off the hydrogen ions, and now that hydrogen becomes positive. So that positive hydrogen ion in the center of this tank with a very high positive voltage now experiences a positive repulsion, which then pushes the particle, now a positive hydrogen called a proton, down the accelerator to the end station where it impacts with the sample. Pretty complicated, but it's kind of fun. It's I like to talk about it as atomic snooker or pool or billiards is how it goes. So we got these little ions that come in and we accelerate them and they interact with the atoms and they scatter just like you would do playing pool or billiards. And then based on the geometry and what scatters off and the energy that comes off, we can work out what elements they are. No, thank you, Armand. So we've had another question come in on the Google form, and it's all around the recent fires that we've had in Australia. As some of you who probably know, for those living in Australia and for those overseas, this summer was a really tough year for the Australian bushfires, and a lot of really pristine bushland was burnt, a lot of animals, houses and people were injured by it. So understanding how these fires happen and the long-term impacts of breathing in that smoke, all the dust, all the smoke that comes up from these fires, how does that impact you is a question that came in. So we're wondering, Armand, if you could tell us a bit more about these fires, the research that you do on the particles, on the final little grains of smoke and sand and dust that get thrown up by these fires, and how that impacts us in our health. Okay. So a whole range of particles are generated from things like bushfires especially, and they're grouped into size fractions. So we have what we call PM 2.5, which is a particulate matter of 2.5 micrometers in diameter and less. And then we have PM 10, which is a slightly larger particle, what we call a coarse particle. And then we have particles greater than that. So the larger particles, the PM 10 and the coarse particles, your body's actually pretty good at blocking those particles out. You have a lot of defense systems within your nose and your lungs, and they also fall out of the air fairly quickly. So you will cough, you will sneeze, it may have a little bit of upper respiratory annoyance, but they don't really go deep in. The very small particles, the PM 2.5 micrometers or less. Now, if you understand what a micrometer is
a millionth of a meter or a thousandth of a millimeter. So if you look at a ruler, look at that millimeter marking, and you divide that into 1,000 times, that's 1 micrometer. So we are looking at that sort of size fraction, pretty well invisible to the human eye. But the problem is that size of particle, your body is not equipped to defend against. So you breathe it in, it goes straight through, deep into your lungs. And once it's deep in your lungs, it can pass into your bloodstream. And once it passes in your bloodstream, then those particles have free access to your body. Now, the issue is that those particles of 1 micron, 2 microns, even less, are about the same size as a bacteria or a virus. So your body responds to those particles like it would a bacteria or virus, and it has an inflammation response. Now, that inflammation response can trigger a whole lot of health conditions that they're just realizing now. So things like not only lung disease or lung issues. In fact, the World Health Organization lists outdoor air pollution as a type 1 carcinogenic, but heart. So that inflammation can put strain on your heart, especially if you have pre-existing conditions, and can trigger heart attacks or heart disease. It can travel up to your brain, and that inflammation, that acute inflammation can trigger stroke. The main issue with air pollution and those fine particles is it has the greatest impact on the people in our community who are elderly and young. So pregnant women, newborn babies, these are where the particles have huge impact, and those who are elderly or who have pre-existing conditions with their heart and other things that can trigger a health response that needs them to be hospitalized or that sort of thing, and can lead to premature death. In fact, there was some, I looked at some research by some scientists looking at the Australian bushfires recently, and they estimate, based on hospital admissions and other things that occurred during that, and looking at the people that came in and excluding all the other potential contributors and narrowing it down to the bushfire, they think that about 400 excess deaths occurred because of the bushfire. So this is on top of what typical deaths around that period would be, an extra 400, which is huge.
Yeah.
So yeah, air pollution is a key contributor globally to premature deaths. And so having people understand about it and look at how they themselves can reduce it is a great thing.
Thank you so much, Armand. I never knew that that all these larger effects that smoke and bushfires and air particle pollution can have. I would almost imagine that this would also impact the animals that were breathing in this smoke as well,
Correct.
which elevates the number of dead and impacted animals that you can imagine from these fires. We have another question coming in now from Lohith, and they're asking, how do you keep these results consistent? So these are the results from your air filter particles. How do you keep them consistent? If a large storm or wind blew a large cloud of soot towards the filters, that could create a massive outlier. So when you do your experiments, when you do your analysis, when you're collecting your samples, how do you avoid such events from interrupting the experiment?
Yeah. So outliers aren't always a bad thing. For example, the bushfires gave huge spikes, huge outliers to what we normally would have seen over the summer period. But the way that our sampler is built is that we have a very tall, probably about a meter or more long stack, a pipe. On that, it has a weather cap on the top. And air is drawn through under that weather cap, down the pipe and into that cyclone that I talked about earlier. So the conditions around don't really affect the kind of sampling. And we have a computer inbuilt on that sampler, which adjusts the airflow, keeps a constant airflow through that cyclone for the 24-hour period. So that's how we make sure that our results are consistent. We also have a lab that weighs every single one of those filters before they go out on a very sensitive balance, and then we weigh them when they come in as well on that same sensitive balance. We have a whole lot of systems built in to make sure that we don't contaminate the filter as they go to a site and they come back. So they get posted to a site fully set up and in a with a cover to prevent contamination. But we also send control filters to the same sites and to other sites to see if they pick up any additional contamination just from the transport. And we analyze those at the same time that we analyze the real filters, and we see if there's any potential contamination that way. So, yeah.
Thank you. We have a question now coming in about the data that you collect. So once you get these filters, you analyze them, you get all these different particles to bounce and scatter or reflect off your filters, and that can tell you exactly what elements are in those filters, in those particles you've collected, but how much of those elements. Once you have that data, you have big sheets of, tables of all your numbers on there, like you would have used in your workshop. Once you have that, where does that data go to get utilized, and what do you do with it?
Okay. So firstly, we should talk about the data itself. What is important to realize about what data we are collecting, the samples that we're collecting, is that they're called receptor particle samples. So the difference is that you have air pollution that is generated from an emission source. So the back of your car, through the tailpipe, through right at a bushfire, maybe at an industry, and they emit or release a range of elements. So we don't measure at the site. What happens is that all those elements get emitted, they go into the atmosphere, and there's a whole lot of mixing that takes place, a whole lot of chemistry that can take place, turning gases into particles, for example. And then those particles are transported. Because their PM 2.5 particles are so small, they can actually reside in the atmosphere for days, if not weeks. If there's no rain, yeah, definitely a couple of weeks they can reside. And because of that, even a gentle breeze, 10 kilometers an hour for a 24-hour period, can take those particles 240 kilometers. Now, if you've got an even stronger breeze, further. So in the recent bushfires, colleagues of ours, of mine, saw smoke and soil particles in New Zealand on the snow. The snow turned brown and red. And they even saw that the particles went all the way to South America. So they can travel very long distances, and they can stay in the atmosphere for that long. Really, gravity takes them down, or if it rains, that can pull them down. So that's the first thing, is that understanding we collect on the other side. So not the samples are emitted, they mix, they get convoluted, they get all mixed up, and then we collect at pretty much ground level at the end. So we get, when we analyze a sample, it's a mixture of all these different sources. So we get 22 different elements in this mixture, and then we have to use mathematical techniques to try and separate all that mixture into the different sources. All right, so we then take that mixture and try and work out how much of that is related to dust storms, and how much is related to bushfires, and how much is related to cars, and how much is related to industry. And that's where the difficulty and the complexity is trying to then unravel that. But it's important that we look at that side, because that's what you're breathing. That's the mixture you're breathing in. You're not breathing straight out of the tailpipe of a car or straight next to a big stack of industry. You're actually breathing this mixture at the end. So that's why we're trying to measure that and understand that. So yeah, so we get that, a big database. We've got a database of probably 70, 80,000 filters, and each of those has 22 or more different elements, and we use statistics to try and work out exactly what's in. So in the workshop, you saw a very simplified small fraction of what that is. It's actually a lot more complicated.
No, definitely. And I'm sure for people who are interested to keep working on workshops like that, ANSTO has lots of great resources you can use to look at more of the data and start playing around with it and figuring out what else you might be able to find hidden in that data. So Pharrell's asked a question now, and they're asking about if you ever test for fugitive emissions. So for those of you who don't know, fugitive emissions refer to usually gases or fine particles that can be released from pressurized tanks or from industry processes. So a really good example of them is when you extract natural gas. So this is gas that's built up underneath the ground that then would eventually get purified and turned to the gas that powers our stovetops and our gas heaters. There's a long pipe from where that gas is emitted, so gas is collected from the ground, to where it's actually collected. And these pipes pipe it all along the way. And as these pipes go, if they have a little crack or a little break in their seal, those emissions, those gases can escape out and go into the atmosphere. So this is a big loss only for industry because they're losing, they're trying to, collect as much gas as they can to sell, and they're losing it as that goes. But this is also really bad for climate change because all these gases are going up into the air. So with that in mind, Armand, do you ever look at fugitive emissions or anything like that in your research?
We don't specifically. So we focus purely on particles, solid particles, because that's what the accelerator can measure. Now, the accelerator, in order for us to accelerate the ions to measure those particles, it has to be under vacuum. Otherwise, those ion beams hit gas particles along the way and they don't fire, and we can't focus them down our accelerator. So the whole accelerator is under vacuum. So any gas that is trapped on the filter gets lost as soon as we put them into the accelerator. So we only focus purely on the solid particles there. But in terms of fugitive emissions, it's quite a broad term, and it really relates to emissions that were unknown, unexpected. So in a way, we do also look at fugitive emissions that are unexpected. That's the point of our research, is to try and identify all these potential sources that we know are emitted, that industries tell us they emit these things, and we check on those, but we also are hoping to identify things that weren't known. And that gives information to regulators like the Environmental Protection Authority and so on to track down and understand where these come from, and hopefully put in place policies or regulations to pull them down or stop them.
Thank you, Armand, and thank you for that question, Pharrell. So the next question comes in from V, and they're asking about the lead. So for those of you who would remember, in the second module of the workshop, it was all around lead emissions. So that's lead that was historically in petrol, how it was, blown out of the back of tailpipes of cars and out of all these emissions from cars. And that was a massive impact on people's health and on the environment. And it's only recently, the last 20 years or so, they've started fading out, putting lead in petrol as they realized how bad that was for the environment. And this question was, which is a very interesting question, I'd love to know your thoughts on it. If lead is extremely toxic, why wasn't it stopped in the 1930s? And why didn't a scientist discover it in their experiments? So I guess it's that broader question of that people knew that lead was dangerous for a lot of time before the 2000s, when they started fading out lead in petrols. Why didn't this happen earlier?
It's a great question, and I don't really have a great response to that. I think sometimes there is a bit of a disconnect between science and the information that we provide and what governments do with that, and how they are able to put in things in place. They have to look at a whole broad range of other things beyond environmental impact and human health impact. They understand that people are inconvenienced in a lot of ways, or don't want to give up certain things, and that's a hard part. And honestly, it's not until this whole COVID issue that I realized that we can, as a global community, be quite severe in what we do to stop issues like this. Prior to this happening, COVID, it would have been. It's hard to actually think that the governments would, for example, if they realize cars are causing a big problem, or tell people we're going to stop cars. There would be an outrage. People need their cars, and they would not, even though they understand the impacts of that to the environment or to health. It's hard for people to forego their comfort or their conveniences. But what I saw is that with this whole COVID and the lockdown, is that myself included, I went out bike riding with my family. Instead of taking the car to the local shops, we all jumped on our bicycles and we went there, and we came back, and it became a great activity. So I could see that we can, if we mobilize and if we make the decision, make those hard decisions to change what we do in order to have a better outcome for everybody.
That's a really good point, Armand. And just on that, something you might have picked up from the workshop was that we had some historic newspaper articles in that workshop. So you would have seen from the early in the 1900s and even in the 1980s, people were still writing articles saying, well, we don't know for sure how dangerous lead really is, even though other scientists were saying, no, like lead is quite dangerous. So that really highlights that scientists, there are lots of different scientists all working on these problems, and they can have different opinions. You know,
Right.
they can not only interpret the data differently, as you might have. You may look at your graph with an outlier, and someone says, "Oh, I think it's a downward trend," and someone says, "No, I think it may look differently." You can have small, you know, differences in opinion like that. But also different people's biases come in as well. If you're a scientist, but you also own a lead petrol factory, even though you may understand the science really well, you may be more hesitant to tell everyone how bad lead is because that'll affect your business. So that's something that as scientists, we have to take into account. What is our personal bias? What you know, bits of information that may not be correct, or maybe, you know, changing the way that we view the hard empirical, the real facts that are in front of us, and make sure that we can remove ourselves from that and really answer the question in its purest form. So thank you, Veer, so much for that question.
Absolutely. Sometimes it's also not just the data, but it's the interpretation of the data that helps you come to a conclusion. And as Luke said, yeah, interpretation of that data can be varied. Absolutely.
Yes, we've got a question coming in from Nan now, and they're asking, did any official government organisation take into account your research and consequently change the methods of particles regarding the number of processes? So I guess that's your, you know, writing all these papers, you're telling the government, all these different organisations around the world about the impacts of air pollution, or what different processes produce the most air pollution. As we saw, it was, you know, for this black carbon, for these tiny bits of carbon that come out the back, mainly of trucks and diesel cars, and people burning fires in their home, having fire-powered heaters, actually produce a lot of this black carbon emissions. So with that in mind, has anything changed with the type of research that you're doing?
Yes, absolutely. So the research, the data set that you saw within the practical workshop was for Mayfield, but our group has collaborated widely. The great thing about science at the moment, it's global collaboration. So we have been involved in a long-term project under the United Nations, looking at air pollution across the Asia Pacific region. So these are involve countries from Mongolia, Pakistan, Bangladesh, all the way down through Australia and into New Zealand. And as part of this project, we've worked with scientists from these different countries doing exactly the same thing that I explained that we've done here in Australia. So collecting samples every week for a 24-hour period, and using techniques like particle accelerators to analyze the elements in those samples and the concentration, and then trying to work out what sources those came from, and then providing that information to governments and environmental protection authorities. And through that project, we saw a whole host of changes. We saw several countries which didn't have air pollution standards or regulations or levels to achieve, implement levels and to reduce their pollution. We saw countries like Indonesia who saw high lead levels that were affecting children, going into children's blood levels, which affect their brain function. They were able to stop several what they call, I think, the battery recycling industries that were emitting these high lead levels. So they basically outlawed that. We saw places like Dhaka limiting or eliminating two-stroke vehicles in their main part of the city because of the amount of pollution that it emitted. So we have seen, based off this research, some actually significant changes in a lot of these developing countries around the world.
Thank you for that. So we have another question coming in from Kate, and it's all around how COVID has impacted the amount of, or the type of particulate matter in the atmosphere. As I'm sure a lot of you will know, that COVID's, you know, totally reduced the amount of people driving on the roads because everyone's working from home. You know, maybe less industry, less people working, producing these kind of things. Have you seen any change in the type of particulates coming out or the amount coming out due to COVID?
Yeah, we are actually still going through that data right now. So because of COVID, ANSTO also was quarantined. So most of us were told to work from home. So for that period, we weren't actually analyzing the data in the accelerator because I wasn't at work, but we were still able to collect some samples. So now that those restrictions have been eased a little bit, me and my colleagues have been busy at ANSTO. I was telling Luke just before we started this session that we've been flat out trying to catch up on analyzing all these samples we collected. But the initial results, so in terms of mass, we have seen a decrease. We've seen an improvement, a reduction in the the PM 2.5 levels because of this less use of cars. People were going to work and so on. That is coming through. So that's the benefit, or the good thing about air pollution, is that it doesn't stay for long. Unlike carbon dioxide and other long-lived climate influences or greenhouse gases, the particles 1 or 2 weeks and then they fall out. The reason they stay up is that we're continually emitting these particles. But if we make changes as a national community or a global community to actually reduce the emission, they will actually come down. The concentration of particles will come down. And so that's a short-term effective way that we can have a significant impact on the particles and their impact on global warming and climate change, and on the environment and on human health, is that we all make that decision to reduce what we emit.
So running off that question, we've got a very poignant question coming in from Lohif, and they're saying that the recent IPCC, that's the Intergovernmental Panel on Climate Change, they released a report stating that we may have gone too far beyond the point of no return in regards to our emissions and climate change. It suggests that even if we stop all emissions right now, we will still face consequences from greenhouse gas emissions and their impact on the climate. Do you have any comments on that?
Yeah, I mean, look, there's two ways of thinking of that, and that report is primarily based on the long-lived climate influences like carbon dioxide, which can stay in the atmosphere for hundreds of years. So that's always very difficult to pull back. Even if we stopped, as you said, as the question said today, we will still be experiencing those effects. But particles are different because they're short-lived. Now, when you compare the influence to climate change between carbon dioxide and black carbon, for example, which is one of the major particles that get emitted, black carbon is actually the second most influential particle, or what's the word? Second most influential thing to climate change after carbon dioxide. If you look at it, there's a term called global warming potential, which is used in the Kyoto Protocol and others, and that's comparing the influence of certain compounds or particles to global warming. And they compare everything back to carbon dioxide. So carbon dioxide, they look at 1 ton of carbon dioxide over an extended period, so 100 years, and they set it at 1. Compared to that, methane, over a 100-year period, the impact to global warming potential is about, I think, 80 or thereabouts. You compare that to black carbon. Now, it's not such a great comparison because black carbon is short-lived, so they have to extend that over a 100-year period, but it's about 900 compared to carbon dioxide of 1. So while carbon dioxide is a long-term issue that will continue on if we were to stop it today, particles like black carbon certainly will have an impact on reducing climate change or the warming if we were to stop it today. Within a couple of weeks, we would see a change. And the reason is that black carbon absorbs efficiently light and then re-radiates that as heat in the infrared. Okay, so when we have a lot of black carbon in the atmosphere, instead of that light being rescattered back into space or other things, it gets absorbed and then re-radiates that as heat. So if you've got it in clouds, instead of the white clouds reflecting some of that solar radiation back into space, those white clouds now absorb because of the black carbon and re-radiate. And sometimes even the black carbon in the clouds can cause those clouds to prematurely evaporate. So then you don't have those white clouds reflecting the radiation back into space. The same with snow. As I said earlier, with the bushfires, we had these smoke and soil particles found in New Zealand on the snow and on the glaciers. Now, snow and ice is normally white. Again, has the albedo to reflect that heat and light back. But when you now change the color to a brown or a black or a gray because of particles that have landed, transported long distance and landed on this snow and ice and glaciers, they now absorb the heat and re-radiate the heat the light, they re-radiate the heat locally, which can cause melting of ice and glaciers and other things. So these are all things within our power to actually stop. So I don't look at it so negatively that we can't do anything. We can always do something. There's always something we can do.
No, definitely. And you would have seen that in the 4th module of the workshop, for those of you who have gotten up to that by now, that there was a scientist who studies the Greenland ice sheet. And I was saying that one of the main things that's accelerating that melting beyond the general global warming was these black carbon particles falling on that ice sheets and melting it. And a lot of that black carbon comes from these big ships that are sort of driving around in that area, transporting goods and freight, and they're putting all that black carbon up into the atmosphere that's falling back down on that snow. So even if, if we stop all greenhouse gas emissions right now, that carbon dioxide would still stay in the atmosphere for a very long time, but that black carbon would slowly start to fall out, which might be bad in the short term, but in the long term, that would really impact the way that our planet absorbs light for the better. So I think there's still a lot of hope there with having some active changes against climate change and the causes of that. We have a question from Pharrell now, and it's talking about what are the most common particles found during the in air sampling. So once you're collecting your air samples, what are some of the most common particles found? Obviously, as you would know, that would change from the different days. If you have a big sandstorm or a fire, that would create a spike in that, an outlier, as you would have seen in the graphs. But generally, what's some of the common particles that you find?
Well, if you think back to the data set you looked at in the practical workshop and the scale, the concentration across the elements that were in that data set, black carbon is really a significant particle that gets emitted across, not only in Australia, but across the world. Black carbon is from incomplete combustion, so it comes out of cars, especially diesel cars. It's funny that diesel vehicles were introduced into the fleet to reduce carbon dioxide levels because they emit less carbon dioxide, but no one took into consideration they emit far more black carbon particles. I mean, you only need to stay behind a big 4-wheel drive when it takes off at the stoplights and see this plume of black smoke that comes out of the exhaust. So yeah, black carbon is a major contributor around the world. A lot of people still use solid fuel for cooking in the household, again emitting black carbon, things like coal and so on. So within Australia, in the Australian context, what we see is in the wintertime, around 60% of the particles are coming from domestic heating. So when everyone in the wintertime turns on their fireplace or their fire pit out in the backyard or that sort of thing, the black carbon and the smoke related to those, we see seasonally every winter about 60% of the PM 2.5 mass that we collect is from that source. In the summertime, we see, and you didn't have this in your data set, but a particle called secondary sulfate. That particle comes from sulfur dioxide, which in the atmosphere reacts with ammonia to form ammonium sulfate particles that we measure. And we see that as the major particle in the summertime period. About 60 to 70% of the PM 2.5 that we measure is from this sulfate. And that comes from coal-fired power stations. So we have several coal-fired power stations and they emit a whole lot of sulfur dioxide into the atmosphere and they convert into ammonium sulfate particles that we then breathe in. So those two areas are what we can do to reduce. So for example, if we decide that we're not going to use our wood fire heaters in the wintertime and reduce that, or switch away from diesel vehicles and to cleaner technologies like electric vehicles, and same with our power generation. If we can move away from coal-fired power, these will all have significant impacts on the concentration of particles that we measure here in Australia.
Thank you, Armand. And I've got a question now out of my own personal curiosity, so I hope everyone's okay with me asking this question. But when you say that you have 60% of the emissions that you're collecting in your samples over winter from black carbon from those fireplaces and stuff inside, how do you account for the inversion layer? So for everyone that's done the workshop, you would realize that when we look at seasonal trends, there's a seasonal trend every year where in the winter you're analyzing more particles, more amounts of particles. And that's not only because maybe more particles are produced in the winter, but also you have a cold layer of air that sits on top of the city or wherever you're trying to measure, and that can trap those particles. So that instead of them getting dispersed out into the broader atmosphere, they get trapped in that particle, which concentrates them and makes the elevator higher. How do you account for this when you're doing your analysis?
Well, we don't really account for it in the sense that we understand that that's contributing. And the main part is we sample at sort of ground level because that's replicates what we breathe in, the kind of air we breathe in. So in the wintertime, when there is an inversion layer and the particles are able to concentrate in that, that's what we're breathing in. So we measure that same thing and we pass that information on. That's really getting the understanding on the health effects, the true health effects on the particles we breathe. Yes, in summertime, the particles can disperse higher and transport further, but that also means we're breathing less of those because they're being transported. They may be transported to other areas that don't normally have those particles, but on the ground level, in the areas that we're sampling, they're not breathing in as high a concentration. But certainly in the wintertime, because of that inversion layer, people are breathing in higher levels of smoke and other things at that level.
No, thank you, Armand. And I think that really goes back to the real reason why you're doing your research is how it affects people and how it affects us. It doesn't matter if it's being trapped there or not. It's what we're experiencing on the ground level, where those samplers are, is what you're really studying as a scientist, which is great. On the note, when we talk about particles and breathing them in, health effects, this is a question from Veer, and it's all around the N95 mask, so masks that we can wear to stop the pollution. And I think it ties back into, at the beginning of the seminar, you mentioned that if you put a air filter out in some very polluted cities, even though you run it for 24 hours, sucking air through that, after 8 hours, they'll get blocked up because it's so full of these particles. So they're asking this question around, why do N95 masks that filter PM 2.5, so that's very small particles, only for 8 hours? So maybe you comment a bit on, do your masks fill up with these particles? Why does that stop?
It's hard to answer that question. It really depends on the kind of PM 2.5 filter the mask is using. If the mask completely blocks up, as we see with the filters we have, once it completely blocks, if we keep drawing air through that, because it's blocked, the filter actually breaks, forms holes, because you're pulling air through something that's already blocked, and it's quite thin of a filter, and that can cause problems. The other possibility is humidity. Remember, our lungs are pretty well 100% humidity, and you've got a sealed mask, sometimes disposable, made of paper and other things. And when you're breathing high humidity into this sealed mask for extended periods of time, that moisture that builds up can degrade the materials and cause them to be ineffective. So that's probably why they put a limit on using those sort of disposal masks for a certain period of time, because they want to make sure that the material retains its integrity and does the job it's designed to do.
Thank you. So this is the question now on to how we may be able to reduce the amount of air particles that we have out there. And they're saying, can we capture and store the air, fire ions at it, and capture the particles, and then release the air again to filter the air? So is there any way, would that be effective? So is there any way that you can use a technique you use to analyze your samples to filter that air so you can start cleaning it? Would that be possible?
Anything's possible. I mean, I don't know personally how, that's a great idea that you'd, as a scientist, come up with that hypothesis and then follow that through. I know things like HEPA filters for purifying air inside the house are very effective. I've got a filter myself, which we got especially because of the bushfires and that sort of thing. So what happens is that these high efficiency particulate filters are able to trap those particles. It pulls it in and then it blows clean air back into the house, especially indoors. Indoors tends to have higher levels of PM 2.5 than outdoors. And it's for a similar reason that we talked about earlier with the inversion layer. The house is a relatively sealed area or volume, and the particles come in because it's not completely sealed. and then they build up in concentration. And as you walk around, and that's what you're resuspending these PM2.5 particles. So, yeah, certainly I know that indoor particulate filters that have a HEPA filter and are designed to stop PM2.5 and are designed for the volume of room are effective. So these are certainly certain ways, but it's the outdoor pollution. We can't. I don't know if we could actually do that. Have filters big enough to start pulling in and cleaning the air and pushing it back out. I'm not sure.
And I guess the best way then to clean the air is to not emit those particles in the first place. So be preventative and have, phase out coal-fired power plants and get some renewable energies in, or have electric cars or more cleaner cars, so we're not actually producing those particles in the first place.
Reducing the amount you use your car. If it's only, they say that most trips for cars are only short distance, 3, 4, 5 kilometers to the local shops or that sort of thing. So maybe make a decision not to do that. If it's a sunny day, jump on your bike and do that instead. And if you can reduce the amount that you're using your vehicle for those short trips, that will all have an impact. It's something that we can choose to do.
Definitely. So I guess this is a question from Veer, and I would assume they're very concerned about your health and safety, because they're asking, wouldn't a cyclone create heat which causes hydrogen to explode? So maybe is that in regard to the heat and amount danger in that you use the cycles? Is it well?
Yeah. Well, hydrogen gas is always something that it's highly explosive, but our instruments for generating the hydrogen ions from the hydrogen gas are designed to prevent this, and we only use very small amounts of the hydrogen gas, so they have a regulator that minimizes that. In terms of the hydrogen that we collect on the filters in the cyclones, again, very, very small amounts on the filter, and they're solid particles, they're not in gas form, so there's no risk there of explosion.
Well, yeah, but thank you for caring about that. It was a really observant question, so thank you. We've covered this a bit, but a question's coming around the way that these particles can diffuse evenly across the atmosphere. As you said, that they don't stay in the atmosphere forever and they drop out after a while. But how long are they in there, and how do they move around the Earth? How long does that take?
Wow. Yeah, they can move very far. As I said earlier, because they can stay in the atmosphere for a couple of weeks if there is no rain, if the conditions are correct, are good for that. Then even a gentle breeze, 10 kilometers an hour, can take these particles 240 kilometers over a 24-hour period. So you multiply that by 2 weeks and how far they can go. I know that we've experienced, and you may remember in the past, that particles that were emitted from volcanic eruptions stopped airplanes from flying because these particles went all the way around the globe. So air travel had to stop because of the potential of these particles destroying the turbines on airplanes and so on. So yeah, the whole reason that I'm involved with the United Nations in this research is that they understand that the particles that one country emits don't stay in that one country. Unfortunately, we're always giving a gift to New Zealand of dust and soil from our dust storms. They often go across and bushfires, and we've seen through our research that the sulfur from China, for example, impacts Vietnam and other countries. We know that there's smoke coming out of Indonesia that impacts Singapore and other countries. So we are a global community when we're trying to tackle air pollution. We cannot just think of ourselves in that silo. What we produce in terms of emissions impacts other countries and communities around us. When we study air pollution, we really look at Australia as a whole, as one big airshed for this pollution, because if there is little rain, as we often get with drought periods and so on, the level pollution of PM2.5 pollution, that is pretty well consistent across all of Australia. So yeah, it really moves quite a long distance. We know that particles can go from Asia to America and other things. So yeah.
But it shows that we're all responsible as global citizens to what we produce. We can't just say it's just going to affect us or our community or even our country, because we're all in this together, and those particles are getting spread around across the world quite efficiently. So we have a question coming in from Noel, and they're asking, have you had any odd or interesting or unexpected results coming from your particle accelerator? Have you ever seen some results come through and been totally surprised or gobsmacked by what's happened?
Yeah, always. That's the interesting part of science. If you could predict always the results you're going to get and you're always right, then it wouldn't be as interesting. What's, for me anyway, the most interesting is getting results that are unexpected, and then having to follow that trail and try and understand and work out exactly why you've seen those results, to redo the test and make sure that it hasn't been something within your test or your setup of the accelerator or your sample that has caused it, but is actually a true result. And then once you understand it's a true result, to do the research needed to understand why. That may be other experiments, that may be setting up more samplers at a site, that may be a number of things. One example, which was also from Mayfield actually, which wasn't in the data set we provided, but we looked at an element called manganese. And we had measured levels of manganese pretty consistently at Mayfield for a number of years. And we didn't know where that was coming from, but we assumed it was some sort of industry source. So we labeled it industrial manganese, and we followed it, and all of a sudden it stopped. I think it was 2008. Our manganese level that we measured on the accelerator dropped pretty well to zero, and then consistently stayed at zero for months after that. So that got us wondering, okay, why did this happen? So we started to have to understand. We redid the analysis on the samples. We checked everything to make sure that it was a real result and wasn't a mistake that we have made on setting up the accelerator or the sample or contamination or something like this. And then when we realized it was real, we started to try and look at what could have caused it. And after researching and searching, we found that there was a manganese dioxide factory in Mayfield that in 2008 stopped. At the height of what they of that factory, they were supplying 15% of manganese dioxide to the world in terms of for alkaline batteries, and then they stopped. And we saw that in the data that manganese dropped off, and that was exciting when we could actually see that we can see some of these things without even knowing ahead of time that that's what happened.
And it's almost like you're a detective, you know, Armand,
Yeah.
because you get this data, you have this problem come that you don't know how to solve, and then you actually have to go out into the real world and try and find that. You research what factories are around in Mayfield, you may go up there and talk to people and really try and figure out what could be the impact of the reason why your data is looking the way it is. Yeah,
Exactly.
which
right.
is so interesting. I guess we've had a few questions come in around your own personal journey to becoming a scientist. You know, I'm sure I'm very excited about the work you do, and I'm sure a lot of people out there are interested and would love to know how to get more involved or what you did to get where you are today.
Yeah.
So maybe you could tell us a bit about that and and what it's like working as a scientist at ANSTO.
Great. Okay. So I did science in high school. I did physics and engineering science for my HSC, and that got me interested in science. I mean, before that, I've always been interested and curious even as a young child. I was that child that annoyed my parents because when I got a new toy, instead of playing with it, I would disassemble it and try and work out how things work, and then fail at putting it back together. And they would say, "Why did you destroy your new toy?" But it's something innate in me that there's always a curiosity as to not just accepting something, but trying to work out for myself, okay, how does that really work? Someone's told me how it works, but I need to see for myself. So that translated into doing physics and engineering science in high school. And then at the end of high school, I went to look at universities, trying to decide what course I would do in university. And at an open day, I remember going past a demonstration at UNSW actually, and it was material science, which I studied within engineering science, and they were looking at a new alloy, a new metal that had a memory. So they could have this piece of metal and they would bend it in all sorts of forms, and if they put that metal into water at a certain temperature, it would come back to the original shape it was, and that interested me. So I decided to study material science at university, and I did that, and I graduated and I did honours in material science at University of Technology, Sydney, and then I got a job at ANSTO. I came out and got a job at ANSTO as a junior scientist. And while I was working at ANSTO, they gave me the opportunity to pursue a PhD. So I did my PhD part-time for 6 years while working full-time at ANSTO. And they supported me to do that. They gave me 1 day a week to be able to go into university and do the experiments, but it was also difficult because I spent many weekends and many evenings poring over data and trying to understand that in order to complete my PhD. But I saw a benefit as well because I was working, and I was working on small accelerators at that time. So these were 1,000 electron volt accelerators compared to what I'm working on now, which are 1,000,000 electron volt accelerators. I was able to work with researchers, and while doing that, I was able to publish papers and improve my CV. And then I finished my PhD in 2013 and have been at ANSTO ever since. I started ANSTO in 2008. So, no, 2005. And I've been there ever since, and I love it. I thought I was only going to stay there for 3 years maybe, but 15 years later, I'm still there, and every day is still interesting and different. Beyond air pollution that I'm involved in driving, that research, I sit with other researchers, maybe like Luke, and from universities and so on, who come and request time on our accelerator to study their samples. And sitting with them inspires me because they tell me about their research, and it's it's contagious when they're excited and they think that their research is going to change the world or have a breakthrough and that sort of thing. Everything from understanding pollution in the waterways in the Great Barrier Reef by studying fish bones, or looking at past tsunamis by analyzing tree rings, or trying to understand the next, how a material failed because of corrosion, maybe of an implant into a body. All these things are, they're super interesting, and that's why I guess I keep coming back to work and I enjoy it. Yeah.
And your excitement is very contagious as well, Armand. You can tell your passion for science and for understanding the world around you really comes out, which is really beautiful. I think something that I love about Armand's story of where he got to today is around how his journey in that PhD wasn't linear. So for a lot of people, like myself, who's currently doing a PhD, you finish your university degree and you go straight on and you don't get much of that real world experience. But Armand's really showed that, there's so many different ways to be a scientist and do research, if you do a PhD or not. But you can also get a job, and while you're working in that job, still do a PhD, still be actively part of the scientific community and be publishing and doing experiments and research and going to conferences. So I think that's very exciting for anyone interested in going and doing studying science, having a career in science. There are so many different ways to go about it.
Yeah, and ANSTO is particularly good at supporting young scientists. I have had a long history. With my undergraduate, I did 6 months of industrial training at ANSTO, and then went back to university. And during my honours, I got a scholarship to actually be on site and do my honours thesis while residing on ANSTO, at ANSTO, working with scientists and so on. So ANSTO has a lot of opportunities from work experience. I've just worked with some work experience students through to industrial training students, honours students. So if you're interested, certainly look at the ANSTO website and look at the opportunities to connect with scientists and do some of these courses.
And for any students that are listening today, ANSTO has an amazing place called the Discovery Centre. And you can go there, you can go and visit with your class or even by yourself, and you have a tour of ANSTO. You can see all these amazing machines, but also learn about the science and what they're doing and how they're changing the world. So for anyone, I really recommend going down to ANSTO and checking it out. At the moment with COVID, the trading hours may be different, but definitely give them a call because it's a really special place to go and visit. So I think that's nearly just the end of our seminar. If there's any other urgent questions, please put them into the chats right now. We probably have time for one more question. But while you're all thinking of those questions, I thought we might just ask Armand one last point.
Okay.
That if you were to give us one piece of wisdom, one little piece of knowledge from this entire seminar for us to take home with it, what would that be? What's the one thing that you want the general public to know about your science and your research?
I think the very fact that you've taken the time to do this practical project, that you were interested enough to click on the project on monitoring air pollution, is for me a fantastic thing. When I started studying air pollution 10 years ago, before studying it, I had no idea. I thought Australia was pristine, clean air, and in many ways we are. I mean, one of the 3 global clean air baseline stations is down in Tasmania. But then I realized after doing this research that Australia is the same as every other country. We have issues of air pollution, even though relatively we are clean. We know that more people die prematurely from air pollution every year in Australia than car accidents. So once you start to understand this and you realize that we can also make a difference and make a change, the hope is that you will look at what you do and make some sort of slight change, whether that is instead of putting on your wood fire heater in the winter, put on a couple extra layers of clothes. Instead of taking your car for that 1 kilometre journey to the local shops, jump on your bike and do that. Yeah, that's hopefully for me the take-home message, that yeah, this will trigger something in you that will help you to make a difference. And we know that we can, as a community, make a difference because of what happened with COVID. Yeah, we can certainly work together and make that difference to the global society.
So thank you, Armand, and thank you everyone for participating today. So this seminar was recorded, so you can go online and watch it later if you want to. We're also having another one this afternoon at 2 p.m. and then another one at 6. So if you have any other questions come up to you that you may well be interested in answering, please save them up for that, or you can send them to the Google form that you would have got a link to in the email, and you can ask that question and we should answer that for you. So once again, thank you all so much, and thank you, Armand, and we'll see you all around. See you later.